Hello and welcome everyone. Today I'll be talking about my most recent and probably most useful project yet. As you may know, these Raspberry Pi single board computers are quite popular, but unlike a regular computer they don't have a real-time clock. So I made a carrier board for one. As you can see, here it is. You might be asking what the rest is. Well, don't worry about it, it's just for charging and managing the battery to make sure that the RTC can run without the Pi being powered on. I'm just kidding, this RTC is just an afterthought, added to my main project, a Raspberry Pi UPS. You might be asking why, considering that those already exist and can be bought for cheap-ish. Well, first of all I want it to be open source, and I want it to be efficient, since as you can see in this schematic, most UPSs do this. They step down the input voltage and then boost it back up to 5 volt again to power the Pi. This is the easiest and most foolproof method, but I wanted something better. This is why I decided to make my implementation completely pass through the input voltage when available. The way this works is with a component called a power mux. Just like a regular mux, it switches between two inputs to one output. But in my implementation, which is based on a TI application node, it's what's called a priority power mux, meaning it has a prioritized input. As you can imagine, the power supply input, which is USB-C by the way, is the one prioritized, and whenever that disappears it switches to the internal boost converter. Thus, when the battery is charged and the power is flowing directly to the Pi, the losses are close to zero and the efficiency is close to 100%. So with these requirements I sat down and came up with a schematic. Breaking it down, it's really simple. The battery charger is just the reference schematic set to 500 mA, charging current by default. Note the 5.1K resistors on the CC lines of the Type-C port. You need those to make sure that your USB PD power supply supplies 3A to this thing. Next, let's look at the burst circuit. As you can see, it's also just a reference schematic with a switch on the enable line. Note how I changed the resistance values to more common ones because I couldn't find these locally where I live, and I didn't want to wait for months to get them from China. The PowerMux design is based on a TI application node. There is nothing special about it. Also, just for fun, I added a DS3231 footprint since the Raspberry Pi has no internal RTC and this thing has a battery already. I didn't film the assembly process since it's quite boring to watch. As you can see in this rod, the battery holder was not even soldered in because I was testing charging current, voltage and so on. Also, what was revealed in this clip is that whenever power is disconnected, the PowerMux goes into a weird oscillation mode that I couldn't quite fix at first. Then lowering the pull-up resistor for one of the MOSFETs helped, but only if you unplug the cable itself. If you unplug the power supply from the wall, it would still oscillate. I realized that it had something to do with the capacitance of the power supply, so as one of my attempts at fixing it, I added a MOSFET that discharges the capacitors with a short pulse. This does work, but it's not perfect, as it shorts out the input through a MOSFET which will probably burn out at some point. So after a bit more experimentation, I figured out that adding a capacitor from one of the PowerMux transistors to the voltage divider of the comparator made it stop oscillating in all circumstances. What I think is happening is that the capacitor creates a negative charge at its output while the first switching of the PowerMux occurs, and rails the input of the comparator for long enough to prevent any sort of oscillation. After this was fixed, I decided to do some more testing and found another issue. The DC to DC converter starts shutting down and power cycling at 2.7 volt, but the battery management IC cuts off the power mux only at 2.5 volts. I decided to try and use one of the unused comparators to make an undervoltage protection circuit. I came up with the following circuit and of course it didn't work, but after a bit more messing around and connecting the supply of the comparator and zener to 5 volt, it all worked. However, a new issue arose when I tried to measure how much current the circuit consumes when powered off. Turns out it was 10 microamps, which is actually quite horrible. For example, the DW01 consumes only 0.1 microamps when powered off. I tried to find the reason for a while, but long story short, it was the BQ battery charger and power management IC. At this point I was thinking to replace it since it doesn't give direct battery voltage readings through I2C, and that's kind of important to know the battery charge level. I looked around and settled for the BQ25895. Since it provides battery voltage reading through I2C just as I want. Also, what I thought is that it might be useful to allow the Pi to shut down the DC to DC converter by using the timed shutdown feature of the BQ chip, which is why I connected the VSys network to the TPS boost IC enable pin. The only remaining problem is the pretty high quiescent current draw of the BQ chip, even though it's a different one. To solve this, I decided to add a simple DW01 and MOSFET pair to the BQ chip. This will cut it off and keep it off until power is provided again via USB-C and prevent the battery from over discharging. At this point I think that is all the useful information I can extract out of the revision 0.1 PCB. So in the next video you will see the next revision that's been described above and how it performs. Thank you for watching and have a great day.